right, so let's put it all together. Now we can calculate torque in a moment of inertia, so let's relate them, right? All right, look at that, huh? Yeah. Oh, that's fun. That is absolutely fun. I put them in backwards. This is so flaky. Now let's back it up and go forward. Let's see what it does. It's crazy. Oh, it's still backwards. All right. So I'm just going to go back and I'm going to say F equals MA. Okay. And then the equivalent is torque is I alpha. Okay. Let's watch that again. Let's see what it does. Does it stop backwards? Yes, it does. Oh, now it goes forward. Okay. So let's just make a little concept map here. Okay. Because these problems can get kind of tricky. Okay. Torque is going to be R times F. Sometimes it's RF sine theta. Okay, but almost always in dynamics problems, it's just R times F, right? Okay, moment of inertia is mr squared if it's a point mass or thin ring. It's 1/2 mr squared. It's 2/5 mr squared, but it's a formula, right, for this, right? So some fraction, 2/3 or something like that, right? And then this guy is our angular acceleration. So we could get that from omega final is omega initial plus alpha times t. We could get it from omega final squared is omega initial squared plus 2 alpha theta, kind of the fraternity right there, right? All of these equations, right? So basically we're going to solve one of these guys, right? We're going to solve one of these equations to do this. Now, keep in mind that a really worthy problem is going to have 4 steps. Step 1, you calculate the torque. Let's just give an example, right? There's lots of variations. You calculate the torque. I tell you the radius and the force. You have to calculate it. I tell you what kind of solid it is. It's a sphere, so you got to figure this out. That's step 2. Step 3, you know this and this, so you calculate this, right? So that's your 3rd step, right? Is you actually use this formula, right? Okay, now you know the acceleration, but I don't just ask you for the acceleration. I say if it starts at rest, after what time does it go through 5 revolutions? Well, now you've got a little kinematics problem to solve. You now know the acceleration from step 1, 2, and 3, and then you know all the rest of it, and you have to solve for the time or whatever it is. Okay. Anyway, let's just look at some of these guys. We'll look at a fully worthy problem, right? Okay. So a string with a tension, this is in the little note guide that maybe you have, with a tension of 2.1 newtons is wrapped around a 5.2 kilogram uniform cylinder with a radius of 12 centimeters. What is the angular acceleration of the cylinder? How many rotations will it make before it reaches a speed of 2,300 RPM from rest? All right. And usually it just asks one question like that, right? So the first thing I'm going to do is if we wrap a string around a cylinder, the string always comes off at right angles to the radius, right? So the first thing I'm going to do is I'm going to find the torque. Torque is just RF, and it's at right angles, right? So I'm just going to multiply that, right? So it's 0.12. That's the radius in meters, right? Times 2.1 newtons. That's meters. And our torque is 0.12 times 2.1, which somewhat surprisingly is 0.252 meter newtons. So now I've got my torque. All right, the next thing I'm going to do is wrap around a cylinder. So we know the radius of the cylinder and the mass. So I got to find the moment of inertia. So I is, for a cylinder, 1/2 mr squared. So it's 1/2 5.2 times 0.12 squared, which is 0.5 times 5.2 times 0.12 squared is 0.03744. And it's small, like so many of our moments of inertia in these complicated times. All right. So now the next thing we're going to do is we're actually going to use the torque as RF formula. I'm sorry, we're going to use the torque as I alpha. So now we're to the crux of the problem, right? Torque is I alpha, so So 0.252 meter newtons is equal to 0.03744 kilogram meters squared times alpha, right? So alpha is, I just have to divide. So this guy, 0.252, enter, divided by the 0.03744 is 6.7307. 0769, etc., right? Radians per second squared. Now we're getting to the important stuff, right? Oh no, how many rotations will it make before it reaches 2300? Let's see. Oh, we have the acceleration. I think we're going to use this guy. Omega final squared is omega initial squared plus 2 alpha theta, right? And we're trying to solve for theta. Theta will, of course, be in radians, but that's an easy fix. Okay, so 2300 RPMs, that's my final velocity. So 2300 times 2 pi divided by 60. That's divided by 60. And we're going to square that, right? Equals 0 squared plus 2 times alpha is this guy, right? 6.730769 times theta. All right, here we go. Are we ready for this? I think we are. So I'm going to go parenthesis 2300 times 2 pi divided by 60, right parenthesis squared divided by 2, divided by that answer that I just got, 4309.4. Now, by this point, we've done one step. Give me my cookie. Nope, you can't have a cookie yet. 2 steps. This is 3 steps. This is our 4th step, right? If you don't count the unit conversions, and then possibly, is this really a 5th step? I don't think so. I'm just got to turn that into, right? So remember to put that in parentheses and you divide. So I'm going to divide that by parenthesis 2 pi. End parenthesis. Whoops, no, that was a 9. Okay, here we go. 685.86 revolutions, right? So this was radians that we got out of this formula, right? Divide by 2 pi, we get that many revolutions. How many sig figs? We only have 2 sig figs, so 690 rev about. All right. Yeah, that's a pretty good example of a problem. I'm pretty sure what's coming up here is some more whiteboard problems. Okay, so go through a few of these things because these are pretty tough.